Stan is a probabilistic programming framework and ecosystem. There are other probabilistic programming frameworks, but Stan is probably the most popular. We've estimated that we have more than 100,000 users. We have 40 plus developers, more than 100 contributors, and we have different interfaces in R, Python, Julia, Scala, Stata, MATLAB, command line, and probably some others. Stan is especially popular in R, so that we have more than 100 R packages built on top of Stan by other people. Example projects where I've been involved and where we have used Stan. First one is a drug dosage modeling with Sebastian Weber and Eero Siivola, where one of the benefits of Stan and probabilistic programming is that we can use these ordinal differential equation models with unknown parameters, and then we can make Bayesian inference for these unknown parameters, and that way we can these models being used then to estimate the drug concentration as function of time. Another example, more recent, modeling political trust in Europe with Marta Kolczynska, Paul Berkner, and Lauren Kennedy, where item response theory models, splines, and post-ratification were used to model political trust, using different polls in different countries, where there was a variation in kind of how these polls were formed, and different population demographics and so on. Instead of these more complex examples, I start with a very simple example demonstrating some of the features of Stan and probabilistic programming. This example is golf putting, and you can see here data from pro golfers putting at different distances, distance from hole measured in feet, and then we have probability of success from different distances, and in addition there's also the raw data mentioned how many putts overall from that distance and how many then went to hole. As these data are probabilities, we couldn't think the usual model for probabilities, logistic regression. The number of successes y is binomially distributed given number of trials n and probability p. And then for each distance we have separate number of successes y and separate number of trials n, and then for each distance we get this probability p. I've here used red color to denote data and green color to denote unknown parameter. And we can then write this y tilde binomial given n and p. And then we want that this probability p depends on the distance, where the distance is also then data. And we use this logit transformation, and so that the logit of that probability has linear model. And then this way we are mapping this linear model with some offset a and slope b times distance between 0 and 1 probabilities. And then we can write this model in Stan language. Here's the model block, and you can see that we can use again this y tilde binomial underscore logit. So here we are mentioning that we are using this logit transformation, and then given n and the formula for this latent linear model. And then Stan can do the inference for this, and we can look at the fit here. In this case, we see that yes, it did get something, but it's not a perfect fit. We could, of course, now, instead of this latent linear model, use something more complex, something like splines, Gaussian processes, neural network, and that way we could get this logistic regression line to go through these most of the data points, some kind of smoothed interpolation. So we could get good bit. But that kind of black box smooth model, yes, it would give us predictions of the probability of success for different distances, but sometimes we can do something better, something which is more directly related to this phenomenon, so that we can use the domain expertise. In this case, we can use just first principle geometry. So on the left hand side you see ball with radius r, and then there's a hole with a radius capital R. There's a distance x, and now you can think of the golf putter aiming to the middle, but to various reasons there's some error in the accuracy, and then the ball might go a bit off from the aim. And now, depending on how much this variation in the angle is and how far the golf put is, these determine, based on geometry, what is the probability that then this ball goes to the hole. And then, because we may assume that there are many different things that which affect this uncertainty in the angle of shot, then we can write this geometry-based model in standard language. You can see here there's a vector of length j, threshold angle, which is just the transformation from the data, r, the radius of the hole, and the small r, radius of the ball, and the distance, which is also vector of length j of these different distances where the puts were made. And then given this threshold angle, and then this unknown sigma for the scale of this angle error, we can compute then vector of probabilities p, and then use again this binomial model and say that this number of successful puts is binomially distributed given n and p. Here we don't use the logic transformation as the previous line is already computing the p so that it is between 0 and 1. Before looking at that, then what we can learn from the data about the sigma, we can just look also at how these the sigma affects then the probability at different distances. And you can see here, so the higher lines are with smaller sigma and the lower lines with larger sigma, and so it seems that there's something useful in that shape. And here, and then we can go look at the fit to the data, and here we have fitted both the logistic regression and then this very simple geometry-based model, and we can see the geometry-based model is doing much better. And so by taking into account this domain expertise, first principle geometry idea, we were able to make quite good fit just with one parameter instead of making the model more flexible and just to non-parametric fit to the data. More recently, there was new data available, and you can see here in this plot the old data with the blue, where the previous geometry-based model was fitting quite well, and then new data, more recent data with the red dots, and we can see that the fit is not that perfect. There seems to be a couple of reasons. One is that the more recent golf putters, pro golfers, are better. They have higher probability of success at the different distances, but also now the data from the shorter distances, we're not able to predict well what happens in the longer distances. So we can do extended geometry-based model by adding distance. we may assume that there's also some inaccuracy in the strength of the put by the golf putter, and then this could also then explain why there was more discrepancy in the model and data, especially for the longer distances. So we can think that the putter aims somewhere behind the hole, and then if it's just slightly too weak or slightly too strong, it's still staying in the going to the hole. But then if it's too weak, it will not reach the hole, or if it's too strong, it will just jump over the hole. And you can see here also then the Stan language for the extended model, where we have then separately probability that the ball goes to the hole based on error in angle or error in distance, and then assuming that these errors are independent from each other, we get then the total probability just by multiplying p angle and p distance. And then use again binomial model to say that we assume that the number of successful puts is binomially distributed given n and this p. And in this case we also have normal 0, 1 prior put on these sigma angle and sigma distance to improve identifiability. And then here you can see the improved fit. So now it is explaining much better also the longer distance putting probability of success. There's still some discrepancy somewhere around 20. And when thinking about this, why there's this error, turns out that these few first observations in very short distance, they have tens of thousands and more than 100,000 puts with probabilities very close to 1. And it happens then that this binomial model is then putting for those very strong influence in the likelihood. But what was missed is that these distances, they are not the actual distances where the puts were made from. They are discretized, so that of course the puts were actually from many different distances and then grouped together. This kind of grouping can then also make a bit of mistake where are the actual these observations. And on the other hand, there's also possibly this additional variation because of these different puts were actually made in different fields, in different weather conditions, and so on. So instead of using this binomial model, now the model is for this raw proportion of the number of successes divided by number of puts from the certain distance, and assume that is normally distributed. And then still use this kind of binomial distribution justified variance, whether you can see here inside the square root, the first part is equal to the variance of binomial model, but then add this additional measurement error variance sigma y squared there. And then having this additional error measurement model, we get very nice fit to the data. Now we could get this much better fit instead of making just the model much more flexible, non-parametric model. There are just 3 parameters. There's the assumed error variation in angle, assumed error variance in distance, and then small additional measurement error component. And we can now learn much more about this, that the angle standard deviation is about 1 degree and distance standard deviation is about 8%. And so we learned much more about the accuracy of these golf putters. And you could, for example, then go and compare your accuracy just from one distance by making several puts and then measuring what was the angle standard deviation of your angle error and your distance error. Of course, this is still a very simplified model. This is not something that would be exact explanation of what is happening. This is currently ignoring what's the friction between ball and grass, and how like the amount of moisture, rain affects it, how long the grass is, what's the inclination of the ground there, and so on. But taking into account that also these putts were made in different conditions, so there were averages over these different environmental factors, it was enough then to be able to explain quite accurately these average probability of successes from the distance with this very simple model, which also then reflects understanding of this phenomenon. The golf example demonstrated use of domain expertise, but it's not necessarily the most impactful example. I did mention earlier also this drug dosage modeling, and there we also were able to use domain expertise. The specific drug is an immunosuppressant used after organ transplants. When the body gets a foreign organ, it recognizes that it's a foreign and tries to reject it, but we can use these immunosuppressant drugs to cool down immune system. At the same time, we want to have enough of this drug in the body that the organ is not rejected, but on the other hand, we don't want to shut down the immune system completely, or otherwise there might be other problems. We can't easily model every cell of the human body, but it turns out that we can make quite good models using ordinal differential equations and simplify the body so that we have gut, and then drug is taken orally, and from gut drug flows to blood system, and from the blood system to interesting organ, and eventually kidney removes this foreign substance drug from the blood circulation, and then the drug concentration lowers in blood system, and then it starts to lower also in this interesting organ. And then this figure here shows with the black line how the drug concentration when you take drug goes up and then eventually goes down. And the good thing is that with this simple ordinal differential equation compartment model, even if we make the observations just at the locations of red circles when we give new dosage, it is possible to learn this rate of flows, and learning this rate of flows in this differential equation model is enough that we can learn then also the behavior of the drug in the body. And so, taking into account this kind of pharmacokinetic model with much less observations, we are able to learn safe drug concentrations. Here, the additional thing was that we had a lot of data for adults, and because for the adults we can make these drug experiments also with the healthy subjects, and then we can learn about how the weight also affects this behavior. And then we wanted to have a model for children, but children are not just small adults, and then extrapolating from the adult data is not simple as that, but we could again then add domain expertise, knowing that there's usually this kind of maturation effect, how the kidney evolves for the children, and then that this maturation effect is usually monotonic, and so that also smaller amount of data from children in cases where they actually had to transplant, and so they had to give some drug, so was able to learn safer dosages for new children. Another quite important recent application for this probabilistic modeling and STAN is COVID-19 modeling. These figures are from Flaxman, Mishra, Candy et al. Paper, and there's a link the website where there are more of these figures and estimates for different countries. And again, taking into account these typical disease models, how contagious diseases behave, and then it's possible to learn from limited amount of observations, seeing, for example, only deaths, try to estimate also number of infections and possible to make forecast and include different prior informations and so on. Next I'm going to talk a bit more about what is going inside STAN. I assume you know basics of Bayesian inference, but to make connection what is when going inside STAN, here's the Bayes rule. I'm now using these colors differently than previous in the STAN language code. So now red is the posterior distribution. So some parameters A and B given data Y is equal then to we have the model term, which at some point was the binomial model Y given A and B, which then when we fix Y and A and B are unknown is the likelihood for A and B, and then we have with green prior for these unknown parameters A and B, and then we divide it by normalization term. We can write this then in STAN language using notation which is quite similar as is often used for writing probabilistic models, so that we have this tilde notation. We say that Y is binomially distributed given n, and then these parameters A and B and data X, but also then there's the logic transformation. And then we are saying that A and B, these parameters, they have a normal distribution prior 0-1 normal distribution. But then what STAN is then doing with this notation is actually this. So this is syntactic sugar for the following. Here now the target is eventually then going to be the log posterior density, and we increment it with these different terms. So first we increment with binomial logit log posterior mass function with Y given n, A, B and X, and here then so this is log posterior mass function because Y is discrete, but then A and B are continuous, and so we get something log density function added to target. And then for these prior parts we add normal log posterior density function A given 0 and 1, and add once for A and once for B. And then now these correspond, instead of building the posterior density, we are building the log posterior density by adding terms of these log likelihoods and log priors. The reason for working in log density scale is that with the floating point number presentation, we get much more accuracy if we stay in log space. Then having this log density, we can sample from the posterior. So there are various algorithms, and then given these posterior draws, we can use them visualize the posterior or compute expectations with these empirical means from the posterior draws. As I said, there are different algorithms. STAN uses dynamic Hamiltonian Monte Carlo, which has good behavior also with large number of parameters. It uses automatic differentiation to compute gradients of the density, which makes this Hamiltonian Monte Carlo very efficient compared to many other Markov chain Monte Carlo algorithms. And I will next show you illustration of this sampling in a simple two-dimensional example, and you can also find the more examples in the link shown. All Markov chain Monte Carlo methods work so that they make this chain where they propose local proposal nearby where they've been, and this Hamiltonian Monte Carlo is doing these local proposals by simulating this Hamiltonian dynamics, kind of bit of physical simulation, as you can see on these curvy lines. And then the nice thing about these Hamiltonian Monte Carlo is that when it is using also the gradients in this simulation, it can sometimes also go quite far away, as you can see from these jumps. In this tutorial I don't have time to go into more details of the Hamiltonian Monte Carlo and what is the dynamic variant of that in Stan, but this will illustrate you anyway the idea of the Monte Carlo draws, that eventually when you get more and more draws, you can see also the marginals starting to resemble more and more the thin-lined true marginals shown in there. So after the model has been written in Stan language, which is then defining this log posterior density, this Stan code is compiled or transpiled to C++, which is then compiled to a binary file for maximum efficiency. Then there's a warm-up phase, which includes also adaptation phase for these parameters of this Hamiltonian Monte Carlo algorithm, and then at some point starts the actual sampling phase. We store these posterior draws. There can be also generated quantities, additional quantities not needed in the actual log density computation. And then when we have collected the posterior draws, we can compute different Markov chain Monte Carlo diagnostics, which will then tell whether this computation worked well. There are many other probabilistic programming frameworks and languages like PyMC3, Turing, .jl, Pyro by Uber, TensorFlow Probability by Google, Perch, Elfie, and so on. In all of these, it is kind of the what does it make that we have specifically something what is called probabilistic programming. So we need to have language which is defined for building probabilistic models. Inference has to be as automatic as possible. We don't want to manually code the inference for every model. Some of these frameworks also support kind of tuning the inference model specifically, or writing bits parts of guiding how the inference can be made more efficient for a specific model, but all of them have also possibility of doing this very automated inference. But then this kind of automated inference, it can't work perfectly for every model and for every posterior. So we need diagnostics that tell if this automatic inference doesn't work, and then we might be able to do something for it. There should be easy workflow to reduce manual work. That's what's the benefit of the probabilistic programming overall. It's not necessarily the fastest possible what you could code up for a specific model, but with easy workflow we can quickly iterate different models, as in golf example, and then manual work is replaced with automation. Stan language is very flexible, so that it's possible to write kind of endless kind of different type of models, which also of course also means that with flexible language there's more work describing even just one model. There are also these domain-specific packages which are built on top of STAN, which provide then simpler syntax for reduced set of model. For example, RStan-ARM and BRMS are R packages which use these simplified R formulas. And so, for example, here, just a linear model predicting temperature given year can be written just in one line. There are also packages within like these RStan-ARM or BRMS are the most downloaded packages, and the third most downloaded package built on top of STAN is this Prophet by Sanjay Taylor while he was working at Facebook for time series. And so having this kind of flexible language engine then makes it easy to make these kind of packages where you can more simply describe that for time series we might want having global trend with possible some change points, holiday effects, weekday effect, day of year effect, and so on. But it's possible to build also new packages and new probabilistic modeling tools on top of this very flexible STAN language. A bit more about the STAN language. It's strongly typed. You can here see data description block, and you can see there's integer and vector types. There's a parameter block with real types, and all this strongly typing helps that it's much easier to catch errors in your model building, so that you will get error warning instead of just failing your computation getting garbage out. STAN has also constraints, so in a data block, if we have these constraints that the lowest value is 0, it can then make check that the data follows these. In parameters block, these constraints in additionally make automatic transformation, so that this dynamic Hamilton and Monte Carlo is working actually in this unconstrained space, even if our quantity of interest is here in the constrained space between 0 and 1. And then previously we had this binomial model a couple of times with binomial logit, but now we could instead define also this P as being constrained, and then this logic transformation happens actually behind the scenes. It's also possible to define functions, and it's possible to have branching, recursion, and so on, which provides great flexibility in defining log densities for models beyond graphical models. For example, here is how to define new generalized Pareto distribution in a function block. So we just define function g Pareto underscore LPDF, which when we are using it would increment then this target as previously discussed. And you can see here in this function we have this if-else branching depending on the value of k, so that we can get a useful result also in the specific case where k is very close to 0 or exactly 0. And then this user-defined function can be used also with this tilde notation, so we can say that y is distributed as g Pareto. But it's good to remember that this was just a syntactic sugar for actually incrementing the log target with this log density. Some of the more advanced features in STAN, I did mention already ordinal differential equations in context of this drug dosage modeling, and STAN is used a lot for pharmacokinetic and dynamic modeling, but there are I've seen also other examples using these ODEs. Algebraic equation solvers belong to the similar category. Hidden Markov models, there's just a recent addition that can handle discrete latent variables by integrating them out analytically inside a function. There's indirect parallelization with some reuse, which is used, for example, in these COVID models to speed up the computation so that it's even for these more complex models possible to get daily updates, daily updated posterior running them in parallel in clusters. There's a lot of GPU support and it's improving all the time. Some interfaces are exposing these log_prob and log_prob_grad so that it's possible to ask log densities and corresponding gradients, and then using that possible to build additional algorithms outside of Stan but still using Stan engine to do the computation. There's optimization with LBFGS algorithm. There's variational inference, which I put in parentheses because the current implementation is not that good, although I know several people who say that they it is useful for them, but we hopefully soon have also more robust inference for this variational inference algorithm. There's a lot more than just this Stan language and inference engine in Stan ecosystem. We have hundreds of pages of documentation and case studies, and very helpful discussion forum, lot of related packages. In addition of these interfaces, we have interactive visualization diagnostics, visualization and model checking, cross-validation, variable selection, and many other packages in R and Python. Stan has some limitations, constraints, and I also then mention possible alternatives. Stan doesn't do sampling for discrete parameters. Stan can be used for many models which are commonly presented with discrete parameters, but then we have many examples showing how we can integrate those discrete parameters out analytically and then use the corresponding model also in Stan. Alternatives could be then like PyMC, tree, Turing, and TensorFlow probability. Stan is not fast for neural networks. It hasn't been specially designed for that, and then Pyro and TensorFlow probability are probably the ones which are fast for them. It's not good for streaming data, at least not yet. There is one group working on making it faster. Birch is not that well known, but probabilistic programming framework, but it's specifically designed for streaming data. Stan is not meant for likelihood pre-inference. For that, I can recommend Elfi, engine for likelihood pre-inference, although there are also some other packages. And here's the end of this quick Stan tutorial. You can find more information on website mcstan.org and the discussion forum discourse.mcstan.org.